Hello again, problem solvers. This is the video for the ice sheet for lesson 16, which is polynomials. And I hope you have the ice sheet in front of you so you can see the problems. I'm just going to say them. I'm not going to write them out here. The first one is that prove that a polynomial degree n can have at most n distinct zeros. This is going to seem a little unnecessary or obvious, but that's okay. So if you take a polynomial that has, say it has, by contradiction, it has n plus 1 or more distinct zeros. Well, zeros mean you can factor it, so you can factor it as, so here's the polynomial, and you've got some leading coefficient, you've got all these linear factors, x minus the 0, x minus the second 0, x minus the last 0, and we said it has n plus 1. Of course, it could have more. Well, then if you multiply it out, the first term is ax to the n plus 1, because there's n plus 1 of these, plus some stuff, and that's not equal to degree n. Okay, so that's a very helpful fact. Just keep in mind that not every polynomial has as many zeros as its degree over r. If you include complex roots, then yes, it always has degree n zeros. But across r, it has at most that many. You can't have more zeros than your degree. Okay, the next one says, find a polynomial with integer coefficients. So we want all the coefficients to be integers, not fractions or irrationals. But it actually has a 0 at, so p of x has integer coefficients, but it has a 0 at root 2 plus root 5. Okay, well, we're gonna create one. And so we know that one element that we're interested in, what you can call it x, you can call it a, whatever you want, is you want this to be an x value that, when you do that, you plug in 0. Well, I know that I don't need irrational roots, or sorry, I don't need irrational numbers, I need integer coefficients, so I'm just going to play with this. I'm going to square it. I don't know where this is going, I'm just trying to get rid of these square roots. 2 plus 2 times square root of 10 plus 5, so 7 plus 2 square root of 10. Okay. I can immediately square this again, but I won't get rid of the square roots. So let's move 7 over. Now if I square again, I get rid of the square roots. So x to the 4th minus 14x squared plus 49 equals 4 times 10, 40. Okay, so if I set this equal to 0, so if I work backwards, this polynomial is not equal to 0, I can work all the way backwards and get x as that. And that's it. It's kind of one of those so easy it's hard type problems. That's a polynomial, right? There's lots of polynomials, infinitely many polynomials that have this as a 0, but this is one that works. I basically just started with the answer and developed the polynomial backwards. And you can check that on a graph or by trying to factor that. Maybe it doesn't factor completely, but it does factor, but it factors over gross numbers. Alright, so let's go to number 3. Okay, we want another polynomial with integer coefficients. We've got some weird fact. We've got the fact that p of 0 equals p of 1 equals 1999, because that's probably the year this problem was on a contest. And it says show that p of x has no integer zeros. Okay, so it sounds like a contradiction proof because you're trying to show something negative. Now, it's a very common trick to shift a polynomial if you're thinking about zeros. So we're going to define a new polynomial. We're going to move the 1999 away. And that's going to make these into zeros of q of x, right? So q of 1 equals q of 0 equals 0. And the reason why I want to do this is because I can factor q at least a little bit. So we had that remainder theorem that it's pretty convoluted about how to do the Euclidean algorithm, but what you know is that basically there's factors and then you have some more stuff, which makes sense, right? If you have 2 0 factors, this is really kind of what we did on the first problem. So q of x has at least two zeros, and it has at least the zero x minus 0, which is x, and then x minus 1. And then it has some sort of remainder, right? And this is really just x. And this is really equal to p of x minus 1999, right? Okay, so now we're trying to do a contradiction. So suppose u is an integer 0 of p of x. We're going to show that's false, so p of u would be 0. So we need to get some sort of contradiction here. Okay, so when you do that, you get p of u minus 1999 equals q of u equals u times u minus 1 times r of u. And keep in mind p of u is 0. That's what we're doing right now. Okay, so negative 1999 equals u times u minus 1 times this. And this is some thing here. And r of x has integer coefficients. That's an important part of this. It's part of the remainder theorem. So the point is that this is a factorization of, well, of negative 1999. But really, of 1999, you can just multiply by negative. However, 1999, in case you didn't know this, is prime. So there's a fun fact, if you didn't know that yet, that's the contradiction. And so kind of pulled that out of our butts, to be honest. But sometimes in these contest type problems, you really got to bring a bunch of facts together. So because that's prime, this is a contradiction, so there are no integer coefficients. But anytime we talk about integers, you should be thinking about factoring in primes, right? Even the lesson on algebraic manipulation, we were doing polynomials with integer coefficients, you should be thinking about factoring in primes in that case. Especially when you see a weird number on a contest, think about how it factors. All right. I am not going to do number 4, and here's why. If you look at number 4, it's an inequality problem, and I'll go ahead and write it down. It's doable, and it's doable with inequalities, and I really need to change this problem because the polynomial way of doing it, so just to say that that's true if and only if that's true, and this is true, and it's true. The polynomial way of doing this is insane, and I would never come up with it, and I've never used it since. But doing this with inequalities is fairly straightforward. If you go this way, that's obvious, right? If A, B, and C are all positive, you get this. If you go the other way, just do contradiction, and suppose one's negative, and you can kind of force one of these to not work. So, for example, if C is negative, well, to this one, 2 of them have to be negative. And then A has to be, then say B and C are negative, then A would have to be more than both of those put together, but that'll mess this one up. So you can chase it around, and you can try that if you want, but you can do it with inequalities by contradiction. There's no reason to use it. If I was doing this on a contest, I would never think to use polynomials, and I shouldn't. It's just an inequality problem. So I'm just going to say scratch this one. All right, but the other 3 are good problems about polynomials.